Okay, so here we are, start of a new unit, graphs of polynomial functions. So polynomial functions for us include linear functions, right? Remember grade 10, y equals mx plus b. Quadratic functions, first two units of 20 dash whatever. And cubic functions, so something new. So let's take a look at this. Part A, the treasurer of the drama club determined the revenue that the club can expect to generate for its next show as a function of the ticket price. So revenue is simply the exact amount of money that's going to come in, right? How much money comes in. The relationship is shown in the table below. So if you charge a ticket price of $0, you're going to get $0. If you charge $1, your revenue is $350, $2, you get $600, and so on. Plot the above data on your graphing calculator. Okay, so here's what we're going to do. Fire up your graphing calculator. Turn it on. I'm just going to clear this. So sometimes it's just a good idea to clear it. So if you're ever having difficulty, so if anything weird happens on your graphing calculator, something's not set, you get some error message you haven't seen before, just clear it. So second plus. So number 7 is reset. You can hit down arrow 6 times, but I'm lazy, so I'm just going to hit 7. We want all. I just go left arrow, it'll go over to there. Hit enter, and then number 2 is reset. And then it says resetting all. Yours takes way longer, but that's how you can be clearing it in the hall and hit that and walk by. So what we want to do is we go to stat, and we want edit. And this is where we're going to enter. So our ticket price is our X value, which goes in list 1. So that's going to be 0, 1, 2, 3, 4, 5, 6. Where does it go to 8? 4, 5, 6. That goes to 8. So just go 0, enter, 1, enter, 2, enter, 3, enter, 5, 6, 7, 8. And then a right arrow just to kick you over to L2. So L2 is always our Y values, right? So our X values are along the X axis. So it says we're putting our ticket price down here. It's like that, right? This is video going. So we've got our ticket price. Okay. So this is our X's. This is our Y's, right? So here's our ticket price down here, and this would be revenue up here. And so our revenue is 0, 350, 600, 750. And you can just look at yours because you've got the whole thing in front of you. But I think it's 600, 350, and 0. So I guess that's saying if you charge $8, nobody's going to come. Right, your revenue will still be 0. You're going to take in no money, nobody's going to buy a ticket. If we're going to plot stuff, we need to set a window. Right? Remember way back when we did the early review sheet, and that we set a window. So for our window, we're going to say, well, our ticket prices go from 0 to 8. And we'll go by 1. And that fits because this goes by 1. Our revenue goes from 0 to 800. And we can go by, let's go by 50s, right? Because we see a 750 there. Really, the scale is among the least of your worries. If you take the scale of 1, you're just going to see a fuzzy axis. It's just going to try and put a scale mark every 1, and it's going to try and put 800, and it won't be able to fit it in. Generally, you want no more than about 20 on the scale. So like, remember your standard window is -10 to 10. It's got 20 ticks. That fits very nicely both directions. Okay, we entered the data. So what we want to do is look at these points, which is, so what we're going to do is this. You go second function, y equals, right? So that's the blue. So we're going into the stat plots. Okay, so it's statistic plots, stat plots. And plot number 1, so you'll be on plot number 1. Just hit enter, then hit enter on, and you'll see that it's now blinking on. And everything else you can leave the same. So the type is a scatter plot. See, the x values are in L1, the y values are in L2. The mark is just going to be a square. So everywhere we enter something, you'll get a square. And it'll be, in this case, it'll be in blue because this is the color. And I'm going to hit graph. And there's our graph. Now you can see just down here, that's the point 0, 0, right? It's drawing a box, but because we said 0, there's 8, 0. And there's 1, and that'll be 350. So if I counted 50, 100, 150, 200, 250, 300, 350. Okay, see how that matches up. So what shape is this? What kind of graph? Right, louder. Parabola, yeah. So it's parabola, it's a quadratic. So graph of data point is called a parabola. Right, we'll throw in brackets here. It's a quadratic. State the window setting. Okay, so we did those. So we're just going to state them. So our x's. So window settings are an ordered triple, which means 3 numbers. And they are x min, x max, x scale, right? So it just follows what's in your calculator. You'll get this on your formula sheet. It'll actually show you x's, x min, x max, x scale. So that if they refer to a graph on the diploma and if they give you the window, you'll be able to see what the window is. If you're graphing as part of a solution on the diploma, give your window, because basically what you want to do is give the marker enough information to duplicate what you've done. In other words, if they enter exactly what you said you entered, they should get the exact same thing that you got. Okay, so we said from 0 to 8 by 1s, and our y's went from 0 to 800 by 50. It's a good window, right? We know that because we looked. Yeah, I mean, maybe you open it up a bit and you go, maybe you go -1 so that you can actually sort of see the axis, but this is fine. Maybe you go up to 1,000 so the 800 point isn't cut off at the top, but it's still there, it's good. So what type of function? Okay, go with quadratic. Yeah. Theory. Determine a possible equation. So to get the equation, we are going to run a regression. So here's the first of the 617 regressions we run. 50 or 60 would not be out of bounds for regression. So you're going to be doing a lot of regression, right? So trying to get these steps down. We're doing one here. We're going to do one here. We'll be doing them tomorrow. Maybe not tomorrow, but we'll be doing them the next day, and the next day, and then the next unit, and then the next unit, and the next unit, right? So regression is a very important part of the course. Okay, so here's how we run a regression. So we're thinking it's a quadratic. So we go to stat, over to calc. Quadreg, number 5, quadreg. You can arrow down or you can just hit a 5. You're going to see one of 2 screens. You either see a screen that looks like this. So who sees a screen that looks like this? Okay, that's a few. Or you will see a screen that says quadreg and then has a bracket. Who sees a screen that just says quadreg and has a bracket? Okay, 1. And then the other 17 people who didn't vote don't see it. If your screen looks like this, you're just going to hit enter on the list and the Y list and the frequency list. Okay, we're going to move down to store reg EQ. If you see quad reg and a bracket, then we're all going to do the same thing at this point. Okay, so if your screen looks like this, you want to be on store. This stands for store regression equation. If you just see the word quad reg and a bracket, we're all going to do the same thing. We're going to go second function, and we're going to go to the vars key over here, just below the down arrow next to the clear. No, we're not. We're just going to hit the vars key. Okay, never mind. No second function. It's been a while. Just hit the vars key. then arrow over to y vars. In other words, it's the variables key. What variables? We want y variables. Okay, it says function, just hit enter on function, and then hit enter on y1. And what that's going to do is put a y1. So either you are looking at a screen that looks like this, or you are looking at a screen that says quadratic bracket y1. If your screen just says quadratic y1, it is defaulting to what you have in the list there, right? So in this calculator base is defaulting to this as well. So the defaults are the X list is in L1, the Y list is in L2. Okay? Older calculators, you don't have to say anything. Now, if you have, I'm gonna pause and then I'll get your question. If your screen looks like this, hit enter to move down to calculate. And then regardless of what your screen looks like, hit enter and it's going to do the regression. And we're back. I never knew we were gone. So here we go. So this is what it says. So when you run a regression, so we run a quadratic regression, we expect a quadratic equation. So our screen looks like this, he says, pointing to the screen, right? Y equals ax squared plus bx plus c. A is negative 50, b is 400, c is 0. Here's what you are going to write. You must write this. You write y is equal to, okay, a is negative 50, so we go negative 50x squared plus 400x. We do not need to write the plus 0, right? If you wrote plus 0, it's just sort of like, yeah, whatever. But you do not need to write it. If the c value was, like 10 or 15 or whatever, then you would write that in. So what I don't want to see is this. I don't want you to give me a screen dump. In other words, do not write down y equals x squared plus bx plus c. A is negative 50, b is 400. You do that, you get 0 marks. Okay, you get 0 marks in class, you get 0 marks on the diploma. So the idea is you must write out the actual function. We're saying it's a quadratic function. We're going to write out a quadratic function. Quadratic function must have y equals. Do not just write down negative 50x squared plus 400x. That's just some kind of an expression, right? But it's not a function or an equation. So we're writing the equation. Y is equal to negative 50x squared plus 400x. Okay. We good? Hang on. Gotta remember how to move. Part B. The base cost to produce the show is $650. However, increasing the quality of the show will increase the cost to stage it. To cover the higher cost, the drama club can increase the ticket price. For each $1 increase in ticket price, the club can spend $25 more on producing the show. Make a table of values to show the relationship between the cost of the show and the ticket price. Okay, use a pencil, fill this in. I'm going to pause. Bing! And this, by magic, it's filled in, right? So $650, for every increase of $1, you can spend $25 more on producing the show. Plot the above data on a graph. Back to the calculator. Turn calculator on. I can clear out of that. I don't need to. So I'm going to go to Stat, Edit. Now, the ticket price is the same. So L1 is still going to be 0, 1, 2, 3, 4, 5, 6, 7, 8. But L2 is going to have different numbers. So I'm just going to go up to the top of L2. And if it's not there, just arrow over. It'll take you there. And start putting in the numbers. So 650, 675, 700, 725, 750, 800. Okay, so we enter all these numbers, so your screen should now look like this. Now, if you have any problems doing this, right, if you're falling behind or anything, don't worry about it. You can watch it at home later and go through it. Slow it down to like half speed. And when calculator things get hit, you can see like little blue glowy stuff and yellow things, I think. So it'll show you which keys are being pressed. So if you're not sure what the heck keys were being pressed here, then slow it down and you can just watch the key presses. Plot the above data on a graph. Oh, see, now that's messed up. So see that 80, if I left, you know what, I'm going to leave that and then we'll fix it, right? So for a window, well, we still want 0 to 8, but for here, it's going from 650 to 850, right? So let's go to window. So 0 to 8 by 1s is fine for the x's. And then, you know what, let's give a little bit of room on either end. So let's say we go from 600 to 900. Okay, now we don't want to go by tens, that would be way too much, right? So let's go by, say, 50. And like that. Oh, that's x res. Never mind, okay. Whoa. Didn't like that. Okay, so really doesn't like that. Okay. X res is always a 1. Okay, so y min is 600, y max is 900. Okay, is your x res 1? Yeah. Never touch x res. Okay, never change it. Because you'll get weird looking things, right? It just don't ever touch it. Just always leave it as a 1. Okay, we're going to go to y equals, and we want to clear out what's in y1, right? Otherwise, we're going to be trying to draw that quadratic on there, and that's not what we have anymore. Since the stat plot is on, and you can tell, because up here you see plot 1, and it's bolded or highlighted, that says that the stat plot is on. So if I hit graph, I should expect to see the points. Okay, and I can see the points, except I don't see a point here.
I see one there.
I know, because you entered your numbers right, but I didn't. So I'm going to go back to stat, and I'm going to go back to edit, and I'm going to look, and I'm going to say, oh, that's supposed to be 825. So like something happened. So there was a gap, and the gap was caused by me having a wrong numbers. That's often a really good reason to look at the stat plot. Okay, there it is, right? Because you see point, blank, and then point. It's like something in here is wrong, right? These appear to be, what kind of graph does this appear to be? Linear. Okay, plot the above data on a graph, check. What type of function? So linear, looks like a straight line. Determine a possible equation. So we are going to run a linear regression. So our second regression of the day. See if I can get this one right. So stat, calc. Linreg, number 4. You're never going to use 8. You're always going to use linreg, number 4. You can arrow down and hit enter, or you can just hit the 4. You are either going to see linreg and an open parenthesis, or you're going to see a screen that looks like this. If it looks like this, just hit enter until you get the store regression equation. If you are looking at linreg and an open parenthesis, we're all going to do the same thing now. But this time we're going to do it right. So vars, over to y vars, enter, enter. So at some point I'm just going to say vars, y vars, enter, enter. Right? So vars, move to the y variable. So we're looking at variables. We want the y variables. We want a function and y1. What we're telling the calculator to do by either having this or seeing linreg y1 is you're saying, I want you to run a linear regression. I want you to take the x values from L1. I want you to take the y values from L2. When you get the equation, I want you to put it or store it in y1. Okay, and then either hit enter or move down to calculate and hit enter. So now it says I run a linear regression. Here's the result. It is to be written in the form y equals ax plus b. Y equals 25x plus 650. Okay, so do not do what I call a screen dump. The screen dump would just be copying it, right? Writing linreg, y equals ax plus b, a is this, b is that. You do that, you get no marks. Okay, because you are not showing an understanding of I'm finding an equation here. And what you want to show is here is a linear equation that could be used to model this data. Okay? Make sense? The videos that are recorded at home are never going to say it makes sense. The ones in class it makes sense like 600 times. We good? I see nodding heads. To the audience out there, people are nodding. Part C. Okay, so a polynomial function. A function that contains only the operations of multiplication and addition. And subtraction is considered addition, right? Like subtraction is just adding the negative. But multiplication and addition or subtraction. With real number coefficients. Coefficients are the things in front of the variables, right? And they have to be real numbers. Whole number exponents. Okay, so you can't have a fractional exponent, right? Like we did earlier, like an exponent of a half is a square root. So a polynomial function will not have any square roots, right? Don't need a square root of x. And two variables. So most of the time we use x and y, right? And we write it as y equals, but I mean, in effect, if we sort of translate here, right, we could write C, the cost, is equal to 25 times T, the ticket price, plus 650. So really, that would be preferable. This is what came out of the calculator. Okay, this is what we should write. We should write which means if we go back up, then we should write R is negative 50 T squared plus 400 T. So if we were graphing this, this would be our T-axis for ticket price. This would be our R-axis for revenue. And we can actually show this, right? So it kind of did this. If we wanted to sketch out the graph, this is what the graph looked like. Right? This was 0. This was 8. This was 800. Okay, so that's our graph, right? That's the graph that we got if we wanted to. Now, this just said determine a possible equation. So at this point, we're going a little beyond what it's asking and just saying, you know, hey, here's your window. There's your equation. Here's what it looks like, right? Here's a picture of it. And then we can kind of do the same thing here by saying, okay, this is ticket price, this is cost, this is your graph, this is 650, this is 850 up here, that's 0, that's 8, right? That's just showing a picture. Hey, here's the graph that we got. Okay, now we're not yet being asked to do that. That's a couple of days down the road when we do the modeling. Then we'll have to write these out. But you know what? It doesn't hurt to see it a bit early. Think of it as foreshadowing. The degree of the function is the greatest exponent of the function. The degree of a polynomial function determines the shape of the graph of the function. Right? Now we're getting into what does the equation look like and what does the graph that goes with that look like. So complete the table on the next page to summarize the properties of polynomial functions. So we are going to start with a constant function. Constant function, which is of degree 0. So a constant function is simply something like y equals 3. So if I go here and I type in, so this is decimals. Did I show you decimals before? Can't remember. Whatever. So this is a website that does graphing. It's called Desmos, DESMOS.com. You can also get, there's a Desmos app you can get for your phone. However, keep in mind, what you have with you on tests and the diploma is your calculator. Okay? This is just nice to show things on because it's got a nice grid and it's all labeled. So So there's the equation y is equal to 3. And on here, watch for scales, right? So what's the scale on here? You go something, 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 2. So the 2 is divided into 4 parts. 2 divided by 4 is a half. So each tick here that's a half, 1, 1.5, 2, 2.5, 3. We almost always assume every tick on a graph is 1, right? So you get a graph on a test, you're just going to probably assume that it's like 1, 2, 3, 4, 5, 6. It may be a half, 1, 1.5, 2, 2.5, 3. So given a graph, always check the scale. And the x scale and the y scale don't have to be the same. So don't assume that because this goes 2, 4, 6, 8, 10, this one might go 5, 10, 15, 20, 25, 30. Okay, so scales, they have to be the same. Every tick on the x-axis must be the same amount. Every tick on the y-axis must be the same amount. But the x ticks don't have to be the same as the y ticks. Okay, so just be aware. If you are given a blank grid on the diploma or on a test and you have to draw something, put your own scale on that grid. Okay, so make sure you put down a scale. So this is like 2, 4, 6, 8, 10. Okay, so that is the graph y equals 3. Where's the thing I want? There it is. So there's a sketch, right? This is the line y is equal to 3. This is the line y is equal to -2. I could do some kind of neat stuff in Desmos. Like I can graph y is equal to a. No, I can't. Never mind. Nothing to see here. Close that. Wrong thing. Not it. Get used to it. A couple days. Look like I know what I'm getting. How many X intercepts does this line have? How many times does it go through the x-axis? 0. How many y intercepts?
0.
Just one line. How many times does this cross the y-axis? Once. The end behavior. So we have quadrants. Quadrant 1, quadrant 2, quadrant 3, quadrant 4. Okay? So it starts in the upper right with quadrant 1, and then it goes that way, counterclockwise. So going around to the left, you have quadrant 2, then down to quadrant 3, then over to quadrant 4. So our end behavior is as we are going from left to right. Okay, so when we're talking about end behavior, as we go from left to right, this line is going from quadrant 2 to quadrant 1. So Q2 to Q1, but this line is going from quadrant 3 to quadrant 4. And so there's a difference here. Now, constant functions aren't really part of the course, right? But it's a good starting point. So you're likely not going to see a pile of questions based on this. Okay? But it's good to know that there is a thing. It's a constant function. It has a degree of 0. It's a horizontal line. Okay? This goes from Q2 to Q1. So somewhere, I think we have the equation. No, we don't have the equation here. We'll write the equation here. Y is equal to K, okay, where K is a constant. So where K is a constant. So in other words, just a number, right? Not a variable, right? It's not like Y equals X. So it's Q2 to Q1 if K is greater than 0. Right? So if K is positive, you're looking at like Y equals 3 or Y equals 5, which would be up here. Y equals 1, Y equals 2. It goes from Q3 to Q4 if K is less than 0. Okay, so it's negative. This one is Y is equal to -2, so it goes Q3 to Q4. Right? It's going across, but it's down underneath. the axis. It could also be, this is the line y equals 0. The line y equals 0 is also known as the x-axis, right? So the x-axis, we're all familiar with, actually has an equation, right? Its equation is y is equal to 0. So in something like y equals -2, you can say, what's that? Well, there is no x, right? There's every x. It says for any x you want to give me, y is equal to -2. What if x is 1,000,000? Y equals -2. What if x is 17.3? Y is equal to -2. What if x is equal to pi? Y is equal to -2. Right? That's what gives us this line here. Domain is the set of all x such that x belongs to the reals. You can put any real number in because there actually is no x in the equation, right? It's just y equals a constant. Your range is the set of all y such that y is equal to k, right? It's just that number. So if you're looking at y equals 3, this horizontal line, then your range is 3, right? That's it. What's the range? 3. What's the range of the one down below there? -2. What's the range of the one you just drew? 0. Now, there is one thing special here, which is except if y equals 0, then there are infinite x intercepts. Right? Because if you're on the x-axis, every single point is an x-intercept. Do not memorize this chart, okay? You don't need to know the constant. What you should just know is that it's a horizontal line. Right? So if you see y equals 3 or y equals 5, so that's a horizontal line. How many turning points? So does this graph turn anywhere? So here we go. Any turns? Nope. Straight line, right? So straight line in linear will have 0 turning points. It won't turn, right? Because it's just a line. It's like driving through Saskatchewan, right? You just hold the wheel. We're never going to turn. You'll be asleep in your Tesla. Doesn't even need to be self-driving, right? Don't do that. We're not condoning driving without paying. Linear function, degree 1. Okay, so this is 10C, right? So in 10C, we were introduced to linear functions. Equation is of the form. So I'm going to write a little strange, right? We would always write that as y is equal to mx plus b, right? Where m was the slope and b was the y-intercept. I'm going to write it as ax plus b, so it just means a is the slope and b is the y-intercept. What's the characteristic of this line here? What's it doing? What do you know about it? Think back 2 years. Say something. Yep.
Positive slope?
Yeah, it's got a positive slope, right? It's got a positive slope, which means that a, the slope, has to be greater than 0. What is this end behavior? So as we go from left to right, we're going from quadrant what to quadrant what? Quadrant 3 to quadrant 1, and what was the characteristic? That the slope had to be positive, right? So a is greater than 0. Okay, so it's saying it rises to the right, right? Goes up to the right. So positive slope goes up to the right. Because slope is defined as rise over run. So if you have a positive rise, you're going up. And if you have a positive run, you're going to the right. Okay, so if you think of a number line, you go to the right, that's moving in a positive direction. Think of the graph, you go up, that's a positive direction. So up here, let's just say A is greater than 0. What can we say about this guy?
A is less than 0.
A is less than 0. So we're going from Q what? So we're starting in Q2, we're going to Q. So if A is greater than 0, we have a positive slope. It's going to go up to the right, which means it's going to go from Q3 to Q1. If you're going up to the right, you're also going down to the left. Right? No, left. Right? Correct? So you think about going down to the left. Down is negative, left is negative. If I take a negative rise divided by a negative run, what's a negative divided by a negative? Positive. Right? So we're still going to get a positive slope, right? Going up to the right or down to the left. We are going down to the right. Down is negative. Negative rise, but a positive run. Negative divided by positive is negative. Up to the left. Positive rise. Negative run. Positive over negative is negative, right? So this is a negative slope. The A value, the slope. Taken individually, each curve has, each line has how many x-intercepts? So this line has how many x-intercepts? This line has how many x-intercepts? So the number of x-intercepts of a linear function will always be 1. Must it always go through the x-axis? Yeah. How come? Well, if it's going to go Q3 to Q1, it has to pass through the axis, right?
Yes.
If it's going to go Q2 to Q4, it has to pass through the axis.
Yes, it does.
There you go. So a linear function will always have exactly one x-intercept. Okay. So the number of x-intercepts is 1. It is exactly 1. How many y-intercepts? 1. What is the y-intercept? Yeah, let's go look at the graph. So I'm going to type in y equals ax plus b. Okay, so here's a neat thing about decimals, right? When you type in variables, so ax plus b, it says you want to add a slider. And so what that means is it's going to start with a and b each being 1. Now I'd rather that b be 0. And get 0.1, b 0. Okay. There's the line y equals x, right? Very first linear function you ever got introduced to, right? There's the line y equals x. Got the 0.11, 2, 2, 4, 4, etc. It's got a positive slope. The slope is 1, right? Go up 2 over 2, go up 1 over 1. Remember your scale. Y-intercept is 0. So now here's a neat thing. I can press play. And we can watch the line. So what's happening to the line? Well, there the slope is positive and it's getting larger. Okay, so there the slope is negative and it's getting larger. There the slope, I'm just going to pause. 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 Can't pause. Pause. Okay. Slope here is 2.93. 2.93 is a positive slope. Positive slope goes up to the right. Slope that goes up to the right, positive slope goes from Q3 to Q1. The larger the slope gets, what can we say about the line? So as the slope gets larger, the line gets steeper, right? As the slope gets smaller, the line gets less steep. If the slope is 0, Why? Okay. If the slope is 0, we have 0x. We're just going to have y is equal to b. We now have a constant function, right? 0x means there's no x. So a linear requires exactly one x in the equation, y equals ax plus b. You can't have 0x because then it just becomes a constant function. If the slope goes negative, what happened to my slider? Okay, if the slope goes negative, okay, it's going down to the right. It's going Q2 to Q4, right? Down to the right. The larger negative it gets, so the larger its magnitude, the larger its size, the steeper the line is. Okay, so let's just go back to a nice slope of 1, which we can do by typing. And we get negative 1. 1. Okay, there's y equals x. What's going to happen if we play with b? Well, line's moving. Which way is it moving? It's either kind of left to right or up and down, right? Like it's because it's a line, you can't really say. If it's a quadratic, you could say, hey, it's going up or down, or it's moving left or right. What we're going to look at is that it's actually moving up or down. Because b is the y-intercept, right? So watch the y-intercept. So here's a y-intercept of 2. Right, here's a y-intercept of 3. Here's a y-intercept of 4. Here's a y-intercept of negative 2. So going back here, there's one y-intercept, and what is it? It is in the equation b. So given the equation, if you're asked what is the intercept, you could say, hey, you gave me y equals 7x plus 12, the y-intercept is 12. You gave me y equals 2x minus 5, the y-intercept is negative 5. Okay, so there is one. If you're asked how many y-intercepts there are, you say every linear function has exactly one y-intercept. Okay, and if you want to know what it is, give me the equation. It is b. What is the domain for a linear function? So what are the possible x values? All of them. What is the range? All y values, right? Because it goes Q3 to Q1, so it's going down forever in quadrant 3. It's going up forever in quadrant 1. It's passing through the axis, which is the value of 0. It is going to cover off all values. How many times does it turn? Straight line. 0. So that table, the table, contains all the characteristics that we're going to look at for all types of functions, right? So every function we describe, polynomials, exponential, logarithmic, sinusoidal, not sinusoidal, it's a little different, but we'll ask stuff about, well, how many x-intercepts are there? How many y-intercepts are there? And can you tell me anything about the y-intercept? Yeah, we can. How many turning points are there? Well, there's this many. What's the domain? This. What's the range? That. What's the end behavior? So every function we look at, we're going to be describing in terms of what's in this chart. Okay? So you're responsible to look at a graph and say, from the graph, I can tell you da, 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 da. And then you're responsible to be like tomorrow, look at an equation, and from the equation, I can tell you da, 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 each of these characteristics, right? Whether I'm looking at a graph or I'm looking at the equation, I can give you all of these characteristics. Okay? Quadratics. So that's about half of your life last year, right? 20 back, whatever. Right? It was all about quadratics. So we know a lot about quadratics, right? So the equation of a quadratic, I don't know why that's not in the chart. Ax squared plus b, start over here. Ax squared plus bx plus c, a is not equal to 0. As long as I'm cleaning stuff up, a is not equal to 0. So just run back up here to linear and just write down a cannot be 0. If a is 0, it becomes a constant function. Okay? If in a quadratic a is 0, that term will be gone. It will become a linear function. So if we want it to be quadratic, we have to have a value in front of the x squared, right? We can't have a 0x squared. Okay, looking at these guys, how many x-intercepts does this have? 0. How many x-intercepts does this have?
1.
How many x-intercepts does this have? 2. So a quadratic can have no x-intercept, 0 x-intercept. How would we know? Well, we know some stuff, right? If it opens up and it is shifted up above the x-axis, then we know there will be no x-intercept. If it opens down and we know that it's shifted down, we know there would be no x-intercept, right? It could open down. So quadratics open up or down. If it just touches the x-axis, then we know it has 1 x-intercept. And if it opens up, but it goes below the x-axis, then we know there's going to be 2 x-intercepts, right? So a quadratic can have no x-intercept, 0, or 1, or 2. So if you're just asked in general, how many x-intercepts can a quadratic have, you say 0, or 1, or 2. If you are given a specific quadratic, you can just graph it and look at it and say there is 1, there is 0, there is 2. How many y-intercepts does this guy have? How many y-intercepts does this guy have? No, keeps going. How many y-intercepts does this guy have? 1. What is the y-intercept? If you see something, say something. See something. It's C. C. Switching to Spanish, C. Why is it C? How do you get the y-intercept? What's the big characteristic? To get the y-intercept, you do what? Set x equal to 0. If you make x 0, what happens to ax squared? What happens to bx? What are you left with? C. Switching to Spanish. C. It is C. Let's hop over to here. Let's not do that. Let's do this. Y equals ax squared plus bx x plus c. I'm going to set b and c to 0. All right, there's your basic quadratic, right? Remember that fateful day, first graph the quadratic, and then time you thought, is this ever going to end with these quadratics? So it's y equals ax squared. It's not even ax squared. It's y is equal to x squared, 1x squared. Basic quadratic, y is equal to x squared. It's got a vertex. It's got an axis of symmetry. Those don't really enter into this course. Okay? So if you're asked to find the vertex, you're just going to do it graphically. You can find the vertex. Right? You'll never really be asked for the axis of symmetry. Sometimes maybe the x-intercepts, because we do have to solve quadratics. So yeah, we might be finding the x-intercepts. I'm going to change one of these at a time. So I'm going to press play on A. So what's happening? Yeah. So there's a stretch going on, right? It's a vertical stretch about the x-axis by a factor of whatever the value of a is. But what happens if a is negative? What's going on? It opens down. If a is positive, it opens up. So our takeaways here are, so it opens up. Right, so for here, we know that a is greater than 0. And for here, we know a is greater than 0. So if a is greater than 0, what's the end behavior? So on the left, where are we? Quadrant 2. And on the right, where are we? So we're going Q2 to Q1 if what? A is greater than 0, right? You already know this, right? Spent all that time studying quadratics. You know if A is greater than 0, it opens up. And now we're saying if it opens up, it goes Q2 to Q1, right? It comes from Q2, comes down, goes back up into Q1. What about this guy here? What can we say about A? Yes, indeed. A is less than 0. And what is the end behavior? Q what? Where does this eventually end up? Q3, and this guy ends up? So if A is greater than, you already know this from before. If A is greater than 0, it opens up. All you got to do is sketch a quadratic opening up, and then you should go through, okay, Q2 to Q1. If A is less than 0, it opens down. Just sketch a quadratic going down and say, okay, Q3 to Q4. What is the domain of quadratic? All real numbers. You're basically saying, what number can you square, multiply by something, and then take another number and multiply it by that same number, right, the bx, and then add a c to it. Well, any number, right? We can square anything. When do we have restrictions? Well, they're all over rationals, right? Because the denominator can't be 0. And you get restrictions when you're doing square roots, because you can't do the square root of a negative. But in a constant function or a linear function or a quadratic, the domain is all real numbers. What is the range? I'm just going to throw in min or max. What does min or max mean? Minimum or maximum, right? So if it opens up, it's got a minimum, right? It's coming down, it's going to reach some value that it can never go below, and then it goes back up again. If it opens down, what has it got? It's got a maximum, right? It's got some number that everything else. So what can we say about the range? So if it has a minimum, what do we know about all these other values? What do they have to be? Yeah, so greater than or equal to the minimum. If it opens down, then what can we say?
It must be less or equal to the maximum.
Right. So the range, if you actually give me something that's on a grid, I can tell you what the range is, right? If I can read the number. If I can graph it, I can use my graphing calculator to find min or max, right? Did that 100 times last year, finding mins or maxes. So if it opens up, it's got a minimum. All the y values must be greater than or equal to that minimum. If it opens down, it's got a maximum. All the y values must be less than or equal to that maximum. How many turning points? One. Can it have more than one? You know, for intercepts, we could have 0 or 1 or 2. So can you have no turning points? No, because then it would just be a line, right? Because no turning point is never going to turn, it's going to be a line. If I have one turn, can I have two turning points? Well, if I have two, it's not a quadratic anymore, right? So quadratic has exactly one, and it must have one. It's not even optional. It's like, yeah, it could have one, two. So number of turning points is one, exactly one turning point. And now for something new. The cubic. Okay, so first new thing. The equation of the cubic will look like ax cubed, and apparently we can't write operate here, plus bx squared plus cx plus d, where a cannot be 0. So if a were 0, you would take out the cube term and you wouldn't have a cubic. You'd have a quadratic, or a linear, or a constant, right? Depending on B or C. So the characteristic for a quadratic is it must have an x squared. Characteristic for linear, it must have an x. Characteristic for a cubic, it must have an x cubed. Here's the cubic. How many x intercepts does this guy have? 1. How many x intercepts does this guy have? 1, 2. And how many x intercepts does this guy have? 3. Let's go play cubic. So I'm just going to do a basic cube. Actually, hang on, let's do this. AX cubed. So right now with A is 1, this is the equation y equals x cubed. This is the basic cubic function. Just like the quadratic, ax squared is the basic quadratic, right? That guy there. This is the basic cubic. It has how many x intercepts? How many y intercepts? 1. So 1 x intercept, y intercept, 1 y intercept. As I hit play, what is the end behavior for this? Q2. Q3 to Q1. Press play. Okay, still 3 to 1, still 3 to 1, still out. Now what is it? 2 to 4. So it's 3 to 1 if what? If A is greater than 0. And it's 2 to 4 if what? Less than 0. Does that look like anything else on that page? Looks like a linear. Looks like a linear. So end behavior, doing that. So it's Q3 to Q1 if A is greater than 0. Q2 to Q4 if A is less than 0. Let's go back and play with this a bit more here. Let's throw on plus D. I'm going to toss in a constant here. Okay, I'm going to take A back to 1 because we should only ever change one thing at a time, right? One. Good enough. Oh, look, D is 1. All right, what's the constant doing? What's D doing? How's it moving? See, this one's obvious it's up and down, right? Because it has that particular little shape there, that little curve in the middle. It's actually moving exactly the same as the linear move, right? But with the linear, it's kind of like, well, it's just a straight line. I can't really tell if it's left, right, or up, down. It really was up, down. It really is kind of both. what? Stop. Pause. There. Move. What's the y-intercept? 2. What's the y-intercept?
3.7.
Now reading the scale. What's the y-intercept? In terms of A, B, C, D, what's the y-intercept? So there is 1, it is D. So the common characteristic of everything we've looked at so far is they all have one y-intercept which is equal to the constant term, right? So if it's just y equals 3, the y-intercept is 3. If it's y equals 2x plus 3, the y-intercept is 3. If it's y equals 7x squared minus 3, the y-intercept is minus 3. So there is one y-intercept. It is always the constant term. We notice that this is the same end behavior, so the same as linear. Okay, so congratulations, life just got easy. You do not have to memorize the end behavior of a cubic. You just have to look at the leading coefficient of a cubic and say its end behavior will be the exact same as a linear with this value for A. Okay? Quadratics you should already know, right? If it opens up, blah, blah. If it opens down, blah, blah. Cubics behave the same as linear. A fourth degree, we don't do fourth degree, but we could ask you about it. A fourth degree has the same end behavior as a quadratic. A sixth degree, or eighth degree, or 10th degree, any even degree has the same end behavior as a quadratic. Any odd degree has the same end behavior as a linear. So if I asked you, what's the end behavior of 6x to the 7th, blah, 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 you would just say, okay, it's an x to the 7th, it's an odd degree, it's going to be the same as a linear. If I had 6x, it would go up to the right. That's from Q3 to Q1, right? So any odd degree has an end behavior the same as linear. Any even degree has the end behavior same as a quadratic. You can scribble that down somewhere in wherever you got a blank space. So that's the same as linear. We don't do fourth degree, we don't do fifth degree. Unless, anybody planning to do 30 guys? No, good. Oh, there's one. Okay. So in 3.1, we will do fourth degree, fifth degree, sixth degree. Now you know. You got a leg up now. You can say 7th degree, the exact same as a linear. 10th degree, the exact same as a quadratic. As far as now, we do say the end behavior a little differently, but not that bad. Domain. What is the domain for this cubic? All the reals. Uh-oh. Okay, good. We'll finish. Okay, we're almost done. Might as well finish. What is the range? So guess what? If it has the same end behavior as a linear, it has the same domain and range as a linear. So every odd degree has that same end behavior as a linear, has the same domain and range as a linear. So nothing new to memorize for cubics. Okay, now, here, we'll just go here. We'll play with this cubic a little bit. I'm just going to throw in like plus 5x squared. So I just want to change its shape, right? So you can see, oh yeah, so cubics can do this. This one has 3 x-intercepts. So how many x-intercepts did we say this has?
1.
How many x-intercepts does this have?
2.
How many x-intercepts? So just by playing with the d value, right, we can take that. It's shape. So cubics mostly for us are going to look like this, right? Have this idea. So if we talk turning points, we have a cubic that looks like this. How many turning points does that have? None. It's not turning, right? It's kind of curving a little, but it has no turning point. Can a cubic have one turning point? No, because then it would be a quadratic. How many turning points does this guy have? 2. So we go to here. Nope. We go to, that's up there. It'll be on YouTube later. You want to see it? Number of turns. Go down. Moving the wrong way. I don't know how to do this anymore. Now that disappeared. Keep going. Keep going. All right. So 0 or 2. You can have no turning point. That's your basic cubic, has 0 turning point. Or 2, you can't have 1. If you had 1, you'd be a quadratic, right? You'd open up or down. If you had 3 turning points, you would become a 4th degree equation, right? So 3 turning points is something that looks like this, right? There's 1, there's 2, there's 3. Uh-oh, right? Both going down. That's got to be even, right? Even degrees, both ends up or both ends down. Odd degrees, whatever. All right.